Hello, everybody. This lecture is on Chapter 4. This week, we're covering Chapter 4, 5, and 6. But 5 and 6 is all on Newton's equations, and that's a total different thing than what we've been doing so far. Chapter 4 is pretty much the culmination of everything we've done up to this point. And then we're going to change gears a little bit. So in Chapter 4, we're covering 4 topics. We're actually going to go back over velocity and position and acceleration in a new way using something called a radial vector. That is going to be something we just know how to do. I'm going to cover it. You're going to formally use the math in later courses, particularly like E&M. We're going to use it. We're going to know we're using it, but we're going to just use it. But today I'm going to talk a lot about how to formally write the radial equation, or the radial vector equation, I should say. And then we'll just be using it. Then we're going to move on to something called relative motion. And the weird thing about relative motion is it's actually really useful. It leads to interesting problems that we're going to talk about. We're going to do homework on it, but it won't be on the exams. It's particularly useful for some things in electro and for certain types of problems. However, the formalism, the mathematical formalism that we're going to use, meaning the way we're going to do the problems, is a bit awkward and clunky. And so I don't expect you to know it that well. I think you need to use it a little bit and be exposed to it. But as far as showing me that you know how to do it, and then in the second part of this, we're going to talk about projectile motion. And projectile motion is essentially free fall if you actually were also moving in the x direction. I'm going to give you a bunch of examples of that, and they're going to be a lot of math. They're going to be overly complicated. In practice, it's pretty easy to do projectile motion, but you really have to do a few problems. However, since there's only so many examples, you can do enough problems. You'll have seen every type of twist to a projectile motion problem, almost. So I'm going to take you through a few of them, and the examples in the book. Between this lecture and the book, you'll have seen pretty much every type of projectile motion problem, and you'll have homework on that. And the last thing we're going to cover is uniform circular motion, also in part 2. We're going to cover that 3 different times in 3 different chapters. So today, I'm not going to derive anything. I'm going to give you the equations. I'm going to explain where they come from, and we're going to use them. And it's going to be plug and chug, put some numbers in. You'll see. Next time we do it, which will be after exam 1, we'll go over it in more detail and derive things. So today I'm doing Chapter 4, Part 1 and 2 for you. I'm going to give you homework on Chapter 4. Tomorrow we'll do Chapter 5. Wednesday, Chapter 6. I'm going to give you homework tomorrow on Chapter 5 and 6. So you're going to have 2 homework assignments this week, but that's because they divide up naturally into different types of problems. The exam will have some kind of constant acceleration, some kind of projectile motion, some type of Newton's equations, Chapter 5, some type of Newton's equations with friction, which is a big change in Chapter 6. So basically, you'll have enough homework problems to see how to do those exam problems. And I'll give you practice exams probably tomorrow night. I want to go through them and make sure they're what I want to give you. But yeah, so you're going to have a lot of homework to do this week and plenty of stuff to study this week. That being said, let's get started on Chapter 4. Okay. So when we talked before about position and vectors and velocity and average velocity and acceleration, we need to kind of change that a little bit. So let's imagine in a y-x plot, I have a particle that is at point 2, 4, and at time 1 second, and then at time 2 seconds, I see that it's at 4, 3. Okay, this is the X and this is the Y position. So let's say it's here, and then it's like here. And this is 1, this is 2, and this is 4. And this is 4, and this is 3 on my graph, right? So this is point 1, and this is point 2. And I want to draw a vector that shows how the position changed, how the particle went from point 1 to point 2. So I just draw an arrow from point 1 to point 2, and I call that the radial vector. How do I figure out what that is? Well, you probably learned you can just subtract stuff, but what we're going to do is we're going to do it as vectors. So from the origin, draw a vector and call that R1. For the radial vector to R1, draw a second vector R2. For the radial vector to R2, and notice that R1 has an X hat component and a Y hat component, and R2 has an X hat component and a Y hat component, okay? But furthermore, when we did vectors, remember we learned how to do vectors by addition, adding vectors. If we start at the origin, if we walk from the tail to the tip, that's a positive. So R1 is positive. Then we walk along R, also positive. And then we're walking backwards from the tip to the origin of R2. So that's negative. And since we arrive back at 0, that's what we get. From this, we can move R1 and R2 over, and we see that R is R1 plus R2. Furthermore, we can see that Rx and Ry is R1x plus R2x and R1y plus R2y. I'm sorry, I'm a little tired. This is not plus, this is, I was thinking of other things. This would be positive minus R1. So this is R2x minus R1x in the X hat or I hat direction. And this is R2y minus R1y in the Y hat direction. And this turns out to be, so this would be 4 minus 2 or 2 in the X hat. And this would be 3 minus 4, which would be minus 1 in the Y hat. So this vector goes over 2 and it goes down 1, right? So it looks something like this. My R vector looks like this. It has a magnitude of Rx squared plus Ry squared. And that would be minus 1 squared is 1, plus 2 squared is 4. So that's square root of 5. And the angle that this makes with the x-axis, the angle is arctan of Ry over Rx. If you put that into a calculator, that would be negative 1/2. So arctan of negative 1/2 is negative 26.56 degrees. It's negative like it should be. We feel good about that. Okay, so all of this, the components of your the components of your R vector are exactly what we've done before. Rx is and Ry, but Rx here is x2 minus x1, and Ry is y2 minus y1. And remember that what we end up here, and I should put these, what we end up with here is we end up with a displacement equation for these guys, okay? Now, we don't have to have something that's so straight between point 1 and point 2. It could be something weird like some exponential curve or whatever. That vector that we drew, this straight line vector, is actually the average change in position, right? So when we do the velocity, remember that the time rate of change is the instant. The average is exactly the vector that points tangential or in the same direction as the path of r, right? So V average is actually R2 minus R1 over the change in time. And we know the change in time was 1 second, and we know what this was. We just found that. This is R over 1 second, right? The instantaneous at any point, and that's why we said that it could look like this or something, where this is 0.2 and this is 0.1, the instantaneous time or the instantaneous velocity is tangent, meaning if I have a curve that looks like this, tangent would be as if the particle didn't turn. It's along the path in a straight line, right? The slope is actually the tangent line to the curve at any point, and the instantaneous is the slope, which is r with respect to t. We'll talk about that right now. Let's imagine in a different formulation of this. So this is pictorial, how you would find it if you had 2 points, but imagine you were given this vector. R of t is 8t in the x hat direction plus 6t minus 4.9 t squared in the y hat direction, okay? The instantaneous velocity at any time of this is the time derivative of this r function. Taking the time derivative of 8t, I get 8 in the x hat, plus time derivative of this is 6, time derivative of this is, bring the 2 down, minus 9.8t in the y hat, okay? And then finally, I can get the acceleration, which is the second derivative with respect to time of r of t, or the first derivative with respect to time of v of t. I see that it's 0 in the x hat direction. This is a constant. This is a constant, so it doesn't factor, but this, the t goes away and I get minus 9.8 in the y, okay? And therefore my acceleration here is minus 9.8 in the y hat direction. There's no acceleration in the x. What this will look like on an x and y graph, so x versus t and y versus t, okay? In the x direction, it's just going to be a straight line. At 0, when time is 0, it's at 0. When time is 1, when time is 2, so when time is 0, it's 0. When time is 1, it's at 8. When time is 2, it's at 16. So this thing's just moving with a slope of 8, which is exactly what this says, that my velocity is 8 times x, or I mean, as a constant 8. So my velocity in the x direction is 8 meters per second in the x hat direction. Obviously, that's what this x means, but I'm writing it again for that. In the y direction, though, let's again do 0, 1, and 2. At time 0 in the y, my position is 0. So I'm also starting at 0. At time 1, this would be 6, and this would be 1 squared, so 6 minus 4.9. This would be something like 1.1. At time 2, this would be 12, but this would be 4. So that would be 16, 19.9 minus 12. So this would be minus 7.9. Okay, so this thing goes up and comes down, right? At any point along this graph, I can draw an arrow that's tangent along the parallel to the path, right? And that will be my velocity. in the y direction at that time. And I can see that my velocity is changing with time. At time 0, it's 6. At time 1, it's actually, I have this drawn badly, but at time 1 second, it would be negative 3.8. At time 2 seconds, it would be 19.6 minus 13.6. So my velocity becomes more and more negative. Even though it starts off and it's initially a little positive, the slope changes. When is it 0? It's 0 when t is equal to 6 divided by 9.8. So a little after 1 second. So from all that, notice too that this I drew as a straight line. In this graph, the velocity at the top of this curve is 0 because the slope is 0. Momentarily, it's 0. This is actually projectile motion because, and I know this graph is labeled, I don't know what it's doing here. Because this graph, I know this slide is labeled acceleration, but that's not what I want to talk about. So if we put them together, and we can assume that y and t, except instead of t, we're going to actually use x, because remember, for every t, we get 8x. So at time 1, we're at 8. And at time 2, we're at 16. And at time 3, we're at 24. And at time 0, we're at 0. So here in the x direction, we're going that way. In the y direction, however, as we saw, we went up, and then we went down, and we shot down. This is projectile motion. You can graph it either way. You could graph it as y versus t, or you can graph it as y versus x with a scaling factor, and it will look like this. Ignore that little squiggle that I made. So in a sense, what we're getting here is we're getting that the position at any point, right, or the position function at any between any two points, or we could find, like we found here, but we don't really need to. What we really need to know is that the position at any time has a x and a y value, and that there's a function that says that r is related to something, let's call it a times the x hat plus b minus c times t bt plus t squared, right, in the y hat. And that this function actually tells us the position in x and y at any time, right? Sorry, there should have been a t. So this function will tell us at any time where the position is in the x and the y directions, okay? That's why we use a radial function, so that we can get all the information in x and y. But note that we can also take them apart, and we could use the r function and the y function. Let me write those as small r's. So we could do r of x and r of y and solve those by themselves, where this is just a t in the x hat, and this is b t minus c t squared in the y hat. And our position at any time is these two things added together, right? We're going to do that over and over again. They're linked by time. They have the same time. The time that appears in the y part of the equation and the time that appears in the x part of the equation is the same exact time. We've taken the equation apart, and we're using an x component and a y component, and we're looking at the motion, and we're showing that x, it goes with constant velocity. Therefore, the slope is a constant number. I shouldn't draw it that way. X would go like that, and the slope of this is a v, so v of x is a constant. And in the y, we're going to get something that looks like this, maybe, where we have something more complicated than x. We'll talk about that later. It's not super important right now. The only thing to really pay attention to is this slide, that you have R. You can find the components of R from this stuff. Or, secondly, that if you're given an equation, R of t, you can take the derivatives of it to get the velocity, and the second derivative to get the acceleration, but you can also break it up into an Rx and an Ry. You can do all this stuff too, where you find the magnitude or you find the angle. We're going to do that a whole bunch of times, which is why I'm kind of glossing over this. But essentially, just know that you can take a vector and you can break it into components and handle the components separately. So the big deal here is, it would be really complicated to try and figure this out sometimes. X and t, or x and y, could have totally different functions. One could be logarithmic and one could be exponential or cosine or something weird like that. But we can break them up and handle the motion in each direction independent of the other direction, linking them through time, because actually the radial vector of the position of the particle depends on the same time all the time. That's the big takeaway that I want you to get here, because that's what we're going to use in projectile motion. We're going to break up and we're going to assume that we can break x and y. We're going to find all the x motion and we're going to find all the y motion, and we're going to equate them by time and link them by time, which it turns out is super useful and allows us to do all sorts of useful stuff if you're an engineer or a scientist or whatever you happen to be. But yeah, there's a few problems that they give you, that they ask you to just find x and y components or find velocities. I would do them. In part 2, it talks about exactly what I talked about. In section 2, there's a thing about how to find R from R1 and R2, and average and instant stuff, and a few key idea stuff. Really, sections 1, 2, and 3 just covers all this stuff, but I think you guys have this. This is really just derivatives from calculus, taking derivatives of the path of a particle. So if you need some review, go through and review it. I'm probably not really going to give you any questions on it. We have better stuff to do. This actually problem solving, and that's problem solving that you should have done in calculus, really. I'm just reviewing it. Okay, now on to the interesting thing in this lecture, relative motion. And relative motion is sections 4.5 and 4.6. I'm sorry, 4.6 and 4.7. They talk about it in one direction and two directions. Really, in one direction is all you need, because the directions are separate, but we'll talk about that. So what is relative motion? And the best example I can start with to give you is, say you're driving in your car, okay? You're driving in your car and you have a book in your lap, and you pick up that book and you put it on the passenger seat next to you. So as far as in the car, you just set it down. You moved it with some speed, but it didn't go anywhere, right? You moved it right to left, some short speed. It wasn't moving at all, at any speed at all. But let's say your car is doing 60 miles an hour, okay? So relative to you, the book was hardly moving, half a mile per hour, whatever, when you set it down. Relative to the ground, the car is moving with a speed of 60 miles per hour. So we assume that there's some origin on the ground, and your car has a v vector of 60 miles per hour moving away from that origin. Now your book relative to the car was hardly moving, if at all, right? When you moved it, set it over. However, your book relative to the ground is moving at 60 miles per hour. And so when you're an observer to motion in another frame of reference, and here the frame of reference would be the car. Essentially, if you're in the rest frame of the car, the book is only moving at half a mile per hour. However, if you're in the rest frame of the earth, you have to take into account that the car is moving as well, and the book was moving at 60 miles per hour. Another way to think about this, let's say you throw, you're driving in a truck, right? And you throw something out of the back. You throw a ball out of the back, right? And someone that's following behind you at the same speed, when you throw this ball at 2 miles per hour, you just toss it, what speed does it hit the ground at? What speed does it hit the car at, right? We need to be able to figure those things out. So we're assuming that if you're both doing 30 miles per hour, right, then relative to your truck and the car behind you aren't moving. You're both doing 30 miles per hour. Relative to each other, neither one of you is moving at all. That might be a little weird. We're going to talk about that. But if you're both moving at the same speed, if you consider the car to be at rest, then you're also at rest because you're moving the same speed in the same direction. And the little chunk of paper that you throw out would hit the car at 2 miles per hour, right? However, to an observer standing at rest on the ground here, it would still see the paper is moving 30 miles per hour in the frame of the truck minus the 2 miles an hour backwards. So it would see the paper suddenly moving at 28 miles per hour away from them. That's a little hard to get your head around. And that's why we need to figure out how do we handle relative motion. These examples are really weird. The examples I'm going to do should be a little bit more clear. But before we do that, we need to do what's called indexing frames of reference, okay? And so what I would like to do is I would like to talk about you are sitting in your car. You're just sitting in your car. So there's the car, and there's the ground. And the ground is stationary, right? And your car is moving 20 miles per hour or 20 or 15 meters per second, whatever you want it to be, I don't care. But the ground is at rest, okay? And so in order to index things, right, we need to give A and B. So we need to say something like V, A versus B. And what are these? This index is, this is a frame of reference at rest, okay? At rest, always at rest. And this is a frame of reference moving relative to that frame. So what do I mean? The car is moving relative to the ground. So I would say V, C versus the ground is equal to, and let's say we are moving at, I said 20 up there, right? So what this is saying is that the car is moving at a velocity of 20 meters or miles per hour to the ground, which is at rest. You are moving relative to the car, what? The car is at rest, you're at rest as well. You have a speed of 0 miles per hour relative to the car. The car is at rest when you're sitting in it, and you're not moving. That's why you're not flying out of the car. You're not being thrown through the windshield or thrown backward out of the truck or whatever this happens to be. You are at rest to the car, which is also at rest in this reference frame. But in this reference frame with the ground, the car is not at rest. So we have these indexes of reference frames. Secondly, we need to talk about what we can do with these. So this is, again, indexing the frames of reference. So we said that the velocity of the car to the ground, if the ground's at rest, was 20 miles per hour. But what if we wanted the car to be at rest and the ground moving? That might take a minute for your brain to think about. But essentially, you could imagine that instead of the car moving at 20 miles per hour, the car is at rest, right? And the ground is moving 20 miles per hour in the opposite direction. But the car is never changing its position. The ground is just moving underneath it. If that were the case, then what we get is that we get negative 20 miles per hour. So that leads to our first idea, and that's that V of A over B is equal to V of B over A with a negative sign. So you can flip these indexes at the cost of a negative sign. Secondly, if we have three, so if we have A, B, and C, three objects or three reference frames, three objects, two reference frames, whatever. V of A over C, V of A over B, now let's do it this way. V of A over C plus V of C over B is equal to V of A over B. So what you do is you cancel these just like you would cancel units, and you get V of A over B, okay? We're gonna do that right now with the car thing again. So if we go back and look, we found that the velocity of the car to the ground, remember the ground is at rest, the car is moving, was 20 miles per hour. And the velocity of U versus the car was 0 miles per hour. And what we wanna know is we wanna know what is the velocity of U to the ground. And so we go U versus the ground is equal to the velocity of U over the car plus the velocity of the car over the ground. And all we have to do is make sure that we can cancel the C's and we get Y over G. And we know what this is. This is 0, this is 20, right? We could also do the ground versus U. And if we did the ground versus U, we would get ground versus car plus velocity of car over U, which happens to be 0. This is negative 20. And these are miles per hour, right? And so that's all we're doing with these frames of references. We're using this weird indexing to help us figure out how to deal with the frames of reference. There's in a weird way, there's a way to draw these with these frame of reference diagrams. And so you can say that this is the ground, right? And then this is the car, okay? And the car's reference frame is actually moving at a velocity of 20 miles per hour. So it's getting further away from the ground in the ground's reference frame. And then you're at some point in the car, but you're not moving. So you have no velocity relative to the car, but the car itself has a velocity relative to the ground. Why we need this is you can choose anywhere you want to be a rest frame. You can assume any point anywhere is at rest, and then figure out what the velocity of objects are in reference to that frame, right? So relative motion means the motion relative to some frame of reference that's at rest. It doesn't actually have to truly be at rest, but you are assuming that it is at rest for your problem. It's an assumption you're making in order to solve the problem. Okay? In 2 dimensions, now your car could be moving with some Y and some X direction relative to a point that is 0, 0 on the ground. If we do that, all we have to do is we say V of X and V of Y, ground, car, ground, car. So all we have to do is we can just figure them out separately and then do the standard V is Vx plus Vy squared, and the angle from the x-axis is arctan. And we'll do that a few times coming up, right? So we can find V we can do in 2 dimensions. We do the same thing that we're doing in 1 dimension. We just note that our V is going to have a component in the X and a component in the Y. And we handle X and Y separately, and we'll put it all together to find our total V. Okay? So let's do an example. This will hopefully help you understand what's going on. In this example, you're traveling north at a velocity of 15 miles per hour. And a truck is heading south at 5 miles per hour. So this is a truck, this is your car, and the ground, we're going to say, is at rest. So, and the ground, okay? So what we want to know is we want to know the velocity of the car relative to the truck and the velocity of the truck relative to the car. When I say relative to, I mean that if the truck were at rest, how fast would the car appear to be going? If you assumed you were at rest in the truck, how fast does the car appear to approach you? If you're at rest in the car, how fast does the truck appear to approach you? We're also going to assume that y is positive upward and negative downward, and that these are y's, okay? That's why this is a negative velocity. So first things first, we also know these are the ground, or the car relative to the ground. The ground is at rest, is 15 miles per hour, positive. And the velocity of the truck relative to the ground is negative 5 miles per hour, okay? And what we want to know is we want to know from these, we want to know what is the car versus the truck, or car relative to the truck. So car relative truck is the velocity of the car relative to the ground, plus the velocity of the ground relative to the truck. Basically what I'm putting in is a G and a G. Car over ground, ground over truck. What are these? Well, I have this. This is 15 miles per hour. The truck relative to the ground is -5. But remember, if I want that, this is the same as minus V of T over G. And that's a minus minus, which is plus 5 miles per hour, which is 20 miles per hour. Let's check ourselves. This is the car relative to the truck if the truck is at rest. So if we assume the truck isn't moving, it would appear, if you woke up suddenly from your nap and you thought you weren't moving, you look, the car is getting closer to you at 20 miles per hour. Even though you are traveling 5 miles per hour south and it's traveling 15 miles per hour north, you put those two things together and it's coming closer to you at a speed of 20 miles per hour. And it's heading up because that's the direction it's heading towards the truck. It's heading toward the truck at 20 miles per hour. Similarly, truck versus car would be truck over ground plus ground versus car. Truck versus ground was -5 miles per hour. Ground versus car, flip that, is -15 miles per hour. And I get -20 miles per hour. Hey, stop. So in this case, the car, if it were at rest, if you were sitting in the car thinking the car wasn't moving, it would appear to you that the truck was approaching you at 20 miles per hour, heading south toward you at 20 miles per hour. That's what this negative sign means, okay? That's it. That's simple. These are the simple rules of relative motion. You can assume either one of them is at rest. You might have to flip a sign, okay? There's a couple problems in your book that do this pretty well. I like this problem. This problem does make things a little bit more complicated. But most of the time with these problems, it's really figuring out what are you talking about. So this says that a plane, there's a wind moving at a speed of, I would have to look this up, sorry. I don't know where I put it. So it probably doesn't matter. There's a wind moving at an angle of 70 degrees or north of east. meaning east is the x-axis, and this is 70 degrees north of east, at 65 kilometers per hour, okay? kmh. And a pilot is trying to fly the plane at 215 kilometers per hour. We don't know what angle he got this thing set on, but that way that he gets his flight path gives him a vector that is due east. So let me try and make this clear to you. A pilot wants to fly due east, okay? There's a wind that is 70 degrees. It's north of east, 70 degrees, and it's 65 kilometers per hour, this wind, okay? And the pilot is pointing his plane at some angle. We don't know what this angle is, but he's flying at 215 kilometers per hour. And what we want to know is, what is the magnitude of this vector, r? Let's actually call it v. And we want to know what this angle is. That angle, the only thing we know is that v is x direction only. It is due east in the x direction only. Okay, so how do we solve this? How do we find what v is given only those two things? Well, before we do anything, let's talk about this. This vector right here, this wind vector, right? It's actually giving us the velocity of the wind versus the ground if the ground were at rest, and that's a bit tricky. We can break this up into v of x and v of y, wind versus ground, and this would be 65 cosine of 70 and 65 sine of 70 degrees, because we know that this thing's making an angle of 70 degrees to the x-axis. Similarly, let's call this is the plane versus the wind. He's flying at 215 miles an hour against the wind, okay, relative to the wind. So the velocity of the plane versus the wind is Vx, plane versus wind, and Vy, plane versus wind. How do you know that it's plane versus wind? Before I do that, let me do this. 215 cos theta, 215 sine theta. Okay, and this is in the x hat, and this is in the y, and this is in the x, and this is in the y. And we know that the velocity of the plane versus the ground, which is what v is in the x hat only. We'll talk about that in a minute. So, I didn't explain this very well, but normally in the problem, it will tell you, the problem's actually in your book, it will tell you that his speed versus the ground, he knows he's traveling due east versus the ground. He's got the plane pointed at some angle where he's doing 215 kilometers per hour against the wind. That's what his plane's measuring, is his airspeed, how fast he's going through the air, no reference to the ground. So what we have is we actually have, this is the velocity of the plane versus the wind. This is the velocity of the wind versus the ground, and we want the velocity of the plane versus the ground. Let me actually write a different G. Okay, so how do we solve this? Well, we solve this by noting that the velocity of the plane versus the ground is the velocity of the plane versus the wind plus the velocity of the wind versus the ground. All you have to do is you P over W, W over G. You can add a W, right? That way when you cancel these, you get them. But remember that we have to do X and Y. So Vx and Vy, which is P versus G and P versus G. Okay? P relative to the ground at rest. P relative to the ground at rest. So this is Vx of the plane versus the wind at rest, Vy, plane versus wind at rest, or in the frame of reference where the wind is at rest, Vx the wind in the reference frame where the ground is at rest, Vy, wind versus ground at rest. And we know that this vector has no y component. That's the key to this whole thing, okay? So once we solve this, we'll be all good. We note that Vx, P versus the wind, we've already solved this. Plane versus the wind is 215, okay? So this is 215 cos of some angle that we don't know yet. We're gonna have to find it. And this is 215 sine of some angle, right? And I should note that these are in the x hat direction and these are in the y hat direction. And then this is 65, so plus 65 cosine of 70 in the x hat. And this is 215 plus 65 sine in the 70, but I'm not done yet. Notice that this should have a negative sign because when I draw my vectors, right, if I draw this triangle here, okay, this is P versus wind, and this is P versus wind in the x hat, and this is P versus wind in the y hat. So as I've drawn it, if this is the x-axis, this has to be a negative value. So what I have is I have that negative 215 sine of some angle is equal, or sorry, plus 65 sine of 70 is equal to 0. Solving this for sine of theta, move that over, move the 215 over. Okay, if I take the arc sine of both sides, I get arc sine of 65 over 215, sine of 70, and that gives me 16.5 degrees. Once I have this, I can plug this in to find V of x P over G is actually V, and that is 215 cos of this angle plus 65 cos 70. And if I put those together, I get 228.4-ish meters per second in the x hat or east direction, okay? So in this problem, and I think there's one that's gonna be in the homework that's the same way, you have to figure out what VP versus the ground is, what V wind versus the ground is, and what V wind versus plane is, or their converse, or G versus P, or G versus wind, or plane versus wind. You need to be able to identify in the problem statement what each of those are. This is an example problem that's given in your book. Go through it, look at it, and try to identify it. When they give this problem, they actually give you this angle as 20 degrees. I moved it to the more familiar 70 degrees. We can talk through this problem at some other point, but for now, the real problem here is the indexing, and that's why I don't like these on exams. It's actually kind of hard to figure out sometimes from a problem statement, what is wind versus ground, what is wind versus plane, what is plane versus wind. It's a mess. It should be easy, and when it is easy, it's super easy to do these problems, but the hard thing is always wording, and too many students get confused by the wording, and I end up having to explain it all, and it's just not worth it. So let's do another problem, which is a boat and a river. This problem is more like a homework problem, but imagine you have a boat, you have a little rowboat, and you can row at 4 meters per second, and you want to go across this 28-meter river. But this river has a current of 6 meters per second, okay? So this is all a river. So you're gonna try and row straight across. Your straight line speed is 4 meters per second, but the river is flowing in the X direction, and you're trying to go in the y direction and go across at 28 meters. We'll talk about that. So the velocity of the river versus the ground, and this is, the ground is someone standing on the shore watching you, sees the river going by at +6 in the x hat, meters per second. And your boat versus the river can do 4 meters per second in the y hat direction, okay? So what is your speed relative to the ground, first of all? Your speed relative to the ground would be the boat relative to the ground. It's the boat relative to the river plus the river relative to the ground. Well, that's obviously 4 meters per second in the y hat. That's your speed versus the river, plus the river versus the ground, 6 meters per second in the x hat. And then I want to know where you're going to end up if this happens as you try to cross it. I want to know where you're actually going to hit the shore. So how do you do that? Well, you know you've got to go 28 meters, right? So remember that velocity is distance over time. We want to solve this for time. So it's x over v. Our x, or in this case, it would be v of x or y over v of y, either one, whichever one you want to use. Here we're going to call this y and this is y. So we get that the time is 28 meters divided by 4 meters per second, which is obviously 7 seconds. Okay, so in 7 seconds, it's going to take you 7 seconds to get all the way across the river. Then to find out how far down you went, again, v of x is equal to x over t, or x is equal to v of x times t. Our x is 6, our time is 7. So our x is 6 in the x hat times 7 seconds, right? Or 42 meters. Therefore, you end up somewhere 42 meters downstream by the time you make it all the way across the river. This problem is done variously as someone trying to swim versus the river, whatever. I purposely made this really easy because the boat only moves in the y, the river moves in the x, so you can see exactly what velocity is doing what. However, you could make this problem harder by putting it at some angle so that as you try to cross, you know, you've got an x and a y component of the boat versus the river and an x and y component of the river versus the shore or the ground. Not too hard though. The last one I want to do is probably the most interesting one. And that is a ball on a train. I'm really hoping that this will help you completely understand not only what we're doing here, but what we're going to do in projectile motion. So in this problem, someone on a train is on a train car, okay? And they're on a train car and they're throwing a ball up and down. So the ball's going up and dropping right back down into their hand. You're just tossing it up. Could be anything, but let's call it a ball. So it's just going up and coming down, up and down, right? Going up, coming down, going up, coming down. Therefore, the velocity of the ball relative to the train is only in the y direction. So the velocity of the ball relative to the train, we're going to say is, well, we'll say it's v naught in the y direction, however fast it starts with, minus g over 2 t squared. This is in the y. I'm sorry, that is wrong. I'm going to take that all back. Your velocity is your initial velocity minus g times t in the y hat direction. So we just multiply it by time, whatever the velocity happened to be at the beginning, and we go from there. Okay? And so from this, let's say we launched it with 6 meters per second is our initial velocity. At any time later, we could figure out how fast it was going. Obviously, we could also use the y equation that we already know, plus v naught of t minus gt squared over 2. And that will give us y at any time, knowing y. But the velocity of the ball in the y, in the train, all it's doing is going up and coming down, going up and coming down, going up and coming down. It goes up, it comes down. That's it, right? Now, the train, however, the train is traveling at 40 meters per second in the x direction, constant speed, okay? Therefore, v of the train versus the ground is 40 meters per second times t. Sorry, not times t. 40 meters per second. Trying to think, how do I want to do this? Since I'm being weird. V in the x direction is x over t, which is, let's say it's 40 meters per second, yeah, 40 m times t. Ooh, I'm sorry, I'm being weird. I'm trying to do something different. I'm trying to do something, set up something for later. But for now, all I want is that in the x direction, it's moving at a constant velocity of 40 meters per second. And that's it. That's our x velocity. Our y velocity depends on time. So our v of t is v naught minus gt in the y hat direction. In the x, it's just that. So if you were standing here on the ground and you wanted to know what the motion of the ball looks like if you were at rest in the frame of reference of the ground, you would have to have the ball versus the train plus the train versus the ground. Now, we already said the ball in the train's frame of reference was moving with v naught minus gt in the y direction only. And the train versus the ground was moving with v of x in the x hat direction, okay? So this is actually v of y, this is v of x. And v of x is just a number, it's 40 meters per second. That's what I was trying to do. But what you see here is that the train relative to the ground is moving in the x direction. It's moving that way, in the x hat direction. So that is v in the x hat. And at the same time, the ball relative to the train is going up and coming down in the y only. So the ball on the train only has y motion. It goes up towards the roof and comes back down and lands in your hand. To an observer on the ground, the observer at rest on the ground, in a rest frame on the ground, sees a combination of both of those. It sees a combination of the ball moving in the frame of reference of the train, and it sees the train's motion relative to the ground, in the ground's frame of reference. And what this looks like is it looks like the ball goes up and comes down in a projectile or parabolic orbit. Okay? Now here's the problem with that I have, and the reason why I wanted to set this up the way I did. Which motion is correct? Is the ball going straight up and down? Or is the ball going on this curved parabolic path? Which motion is true? If you were in the train and all the windows were closed or there were no windows on the train car and you were sitting in the train car tossing something up and down into your hand, tossing it up and catching, tossing it up and catching, it most definitely is going up and coming back down and going up and coming back down in one dimension. However, that's because you're both in the same rest frame. You're both at rest according to the train, right? However, because I'm an observer and I'm on the ground, I also see that the train is in motion. And if I can see through a window, I would see the ball would be doing this parabolic path. So it's a combination because I've chosen a different rest frame. And you might think, but this has some real implications. My final thoughts on this, these real implications. You could mathematically decide that you are the center of the universe and you are at rest. And everything else around you is moving relative to you being at rest. Obviously, that doesn't make a whole lot of sense because you can move your arms and stuff, but you could actually assume that the sky is rotating around you, that everyone who moves is moving relative to you, that the sun is rotating around your point. It would be really ugly and complicated, obviously. But it's completely valid to say that you're the center of the universe if you want to do the math to get you there. Another one that's kind of interesting to illustrate this is the moon. We all know that the moon goes around the Earth, right? So the Earth's here and the moon rotates around in a circle. It orbits the Earth, right? Well, what about the sun? How does the moon orbit the sun? And it orbits the sun the same way, right? However, if the Earth wasn't there, right? What you would actually see is that the moon begins here, and in the next part, it's moved a little bit further, and in the next part, it's moved a little bit further, and in the next part, it's over here, and in the next part, it's over here, and in the next part, it's over here. Next part, it's over here, let's say. The next part, it's over here. Next part, it's over here. Next part, it's over here. And what you see is that the moon kind of does this sine wave curve around the sun. The moon, from the point of view where you're at rest on the Earth, the moon orbits the Earth in a circular path. The moon orbits the sun. The Earth orbits the sun in a circle. The moon orbits the sun in this weird kind of sine wave that goes back and forth. And what I'm trying to get at is that motion, this sine wave motion, looks very different than what we traditionally think the moon is doing. If you draw it out, and this isn't the greatest drawing ever, but basically what you see is as it goes around the sun, the moon is swinging back and forth around the Earth. And this path is swinging back and forth with the Earth as the Earth spins. And that's how we get that motion where it's orbiting us. We're dancing together in a much more complicated motion than it looks like from the rest frame of the Earth. Are there natural rest frames? Yeah, there are true rest frames. There are ways to tell, for example, that the Earth is rotating. There are ways to tell that the Earth is rotating around the sun. So there's kind of an idea of real motion, but it gets complicated. It's for much later studies of things, studies of mechanics and dynamics. But you can always look it up on Wikipedia or Google it. How do we know that the Earth is actually rotating and not at rest? How do we know that we don't live in a universe where the Earth is at rest and the sun's rotating around us and the planets are rotating around us? I mean, obviously, it makes sense that the most logical answer would be that the planets rotate around the sun because the sun's bigger. But in a sense, what if the solar system was actually rotating around the Earth and the Earth was standing still? It sounds like a dumb, unintelligent question, but mathematically, you could assume the Earth was at rest and find the relative velocities of everything relative to a rest frame where the Earth is at rest. This idea of a train car with all the windows closed and the ball going up and down is actually the basis that leads into Einstein's theory of relativity and why the speed of light is a constant and what is actually going on with gravity, what gravity is. Because Einstein basically said that if you were in an elevator in the middle of space, an elevator meaning if you were in a box that you couldn't see out of, you were just standing in a box, and it began accelerating, you could not tell the difference between that acceleration and gravity. The relative acceleration is the same as if you were under the influence of gravity and falling. So that's kind of where we need to leave this for now, is that motion is relative. It's always relative to some preferred frame of reference. We're going to do a bunch of projectile motion. And in that projectile motion, we're going to assume that we're standing at the ground at rest and the object shoots up and comes back down. And that this velocity is relative to our rest frame, okay? And it's something that becomes much more complicated because in physics, we're always trying to find some tool, some way that we can solve problems that we don't have enough information. So we're always trying to find another way. And one very useful thing is sometimes in a frame of reference, we're going to find that in a rest frame of a body, because it's not moving, it's easier to solve the equations of the motion for it. It's just something that we need to keep in mind. So go back and look at the car and the truck example. Look at the boat and the river example. The plane example probably isn't all that helpful. It's a little too complicated, but the boat and the river and the car and the truck definitely show you how to use relative motion and to be more precise about what you're talking about. Are you at rest in the car? Are you at rest in the truck? And are you at rest on the ground? Are you at rest on the ground or in the river or in the boat? So just think about those things and think about what they mean and understand that later on you're going to have to figure out sometimes relative motion in things that are in different rest frames. And it gets complicated, but for now, the relative motion stuff will not be on the exam. You will get a couple homework problems. They should be pretty easy, I hope. So this is the end of part 1. Part 2 is going to be all about projectile motion. I'm going to take a quick break and I'll get back at it.